Good day, everyone. We are going to discuss Petrogenesis. So let's take a look and see what Petrogenesis is all about. What is petrogenesis? Petrogenesis, also known as petrogeny, is a branch of petrology dealing with the origin and formation of rocks. While the word petrogenesis is most commonly used to refer to the processes that form igneous rocks, it can also include metamorphic and sedimentary processes, including diagenesis and metamorphic reactions. Petrogenesis of an igneous rock comprises three successive stages: magma generation, magma differentiation, and assimilation of crust. The three successive stages of petrogenesis. Magma generation. There are two primary ways that magma can be formed. Magma is formed by both wet and dry melting processes. By melting different parts of the layers of the earth, basaltic, rhyolitic, and andesitic, magma will be formed. The composition of magma depends on the rock it was formed from and the condition of that melting. Magmas derived from the mantle have higher levels of iron, magnesium, and calcium, but they are still likely to be dominated by oxygen and silicon. That is complete melting, not partial melting. Magma differentiation. Differentiation is the process by which magmas evolve to give rise to a variety of magmas and rock types. Therefore, certain physical processes are required to cause the chemical diversification of a magma. Any process that causes magma composition to change is called magmatic differentiation. Over the years, various processes have been suggested to explain the variation of magma compositions observed within smaller regions. Among the processes are distinct melting events from distinct sources, various degrees of partial melting from the same source, crystal fractionation, mixing of two or more magmas, assimilation or contamination of magmas by crustal rocks, liquid immiscibility. Assimilation of crust. Because the composition of the crust is generally different from the composition of magmas, which must pass through the crust to reach the surface, there is always the possibility that reaction between the crust and the magma could take place. If crustal rocks are picked up, incorporated into the magma, and dissolved to become part of the magma, we say that the crustal rocks have been assimilated by the magma. If the magma absorbs part of the rock through which it passes, we say that the magma has become contaminated by the crust. Either of these processes would produce a change in the chemical composition of the magma, unless the material being added has the same chemical composition as the magma. In a sense, both assimilation will produce some of the same effects as mixing, but it is more complicated than mixing because of the heat balance involved. In order to assimilate the country rock, enough heat must be provided to first raise the country rock to its solidus temperature, where it will begin to melt, and then further heat must be added to change from the solid state to the liquid state. The only source of this heat, of course, is the magma itself. Let's imagine a simple case of a pure mineral making up the country rock that is to be assimilated. In order to raise the temperature of the country rock from its initial temperature to its melting temperature, heat must be provided. The amount of heat required is determined by the heat capacity of the rock. Once the temperature has risen to melting temperature, further heat must be added to melt the rock. This heat is known as the heat of melting, also sometimes called the latent heat of fusion. As stated above, the heat required for this process must be supplied by the magma. In our example, we will take a simple case where the magma has a eutectic composition and therefore melts at a single temperature. This time, we will assume that the magma is at a temperature somewhat above its melting temperature. In order to provide the heat for assimilation, it would first have to cool. Once it reached melting temperature, the only other source of heat must be provided by crystallization to release the latent heat of crystallization. Note that in the case shown here, the total heat released by the magma in cooling to melting temperature and crystallizing is still not enough to melt the country rock. Furthermore, in this process, the magma has completely crystallized, so assimilation cannot take place. There are two ways to overcome this problem. 1. If the initial temperature of the magma were much higher, then it could provide the heat by simply cooling to its melting temperature. This is unrealistic. However, because magmas are probably relatively close to or below their liquidus temperature after having passed through cooler country rocks. 2. If the country rock had an initial temperature closer to its melting temperature, less heat would have to be provided by the magma. This could happen if there were successive batches of magma passing through and releasing heat into the country rock. Nevertheless, this heat budget analysis illustrates the difficulty involved in bulk assimilation of country rock by magmas and makes the process less attractive as a process to explain the chemical diversity of soot rocks. Note also that the heat budget will still likely involve crystallizing some of the magma, so assimilation takes place. It will likely involve a combined process of crystal fractionation and assimilation. In a more realistic, natural situation, things will be slightly different because both the country rock and the magma will melt or crystallize over a range of temperature, rather than at a single temperature. Even still, the amount of heat required to melt the rock must be provided over a relatively narrow range of temperature. But partial assimilation of the country rock would be possible because the country rock would only have to be partially melted to produce a liquid that could mix with the magma. In this case, we would say that the magma has been contaminated by the count. Application of trace elements to igneous petrogenesis. Trace elements are those which occur in very low concentrations in common rocks. Their concentrations are therefore commonly expressed in parts per million. Unlike major elements, trace elements tend to concentrate in fewer minerals and are therefore more useful in formulating models for magmatic differentiation. And in some cases, in predicting the source of particular magma, trace elements most commonly used for the interpretation of the Petrogenesis of igneous rocks. Keep in mind that the concentration of trace elements will vary with the rock type, whereas nickel and chromium show higher concentrations in mafic and ultramafic rocks. Zirconium and rubidium are more concentrated in acidic rocks. Accordingly, some major or minor elements as potassium and phosphorus, which occur in very low concentrations in basalts, are just as useful in petrogenetic interpretation as some trace elements. The incorporation of a trace element in the crystal structure of one or more minerals depends largely on its charge and radius, but also on the electronegativity of this element and crystal fields effects. Accordingly, a trace element will either substitute for a major element in the structure of a crystallizing mineral or remain in the liquid. Types of trace elements. The types of trace elements are large ion lithophile elements, high field strength elements, transition elements, and rare earth elements. Application of trace elements to igneous petrogenesis. 1. Testing models of magmatic differentiation using trace elements. 2. Determination of the depth of generation of a primary magma. 3. Prediction of the phases fractionating from a magma. 4. REE and REE diagrams. 5. Discriminant diagrams.